Hi everyone. Now I'm going to go over the example problem. This is example 6.2 in your textbook in page 206. So the question is a 12-foot long vertical cantilever, a 4-inch nominal diameter standard pipe support a 5,200 weight attached at the tip of the pipe. So it looks something like this. I'm going to share my screen. Okay, here we go. So this is simple drawing of the problem. So here we have a weight, and this is 5,200 pounds. And then this is a steel pipe. And the nominal diameter is 4-inch, but the cross section looks something like this. So here we have, this is a hollow section. So the outer diameter, DO, is, let's see, 4.5. Okay, so 4.5 inches. The I, the inner diameter, which is this, is going to be 4.026 inch. Okay, so the thickness is 0.237 inches. And the height of this pipe up to the center of this mass is 12 feet. So this is a given information for the problem. All right, so the material properties. So the moment of inertia of this pipe about this centroidal axis is given as I is equal to 7.23 inch to the fourth. And elastic modulus, Young's modulus, is 29,000 KSI. And the weight of this pipe is given as 10.79 pound per unit length, which is feet. So the question is, determine the peak deformation. So here's the question. Determine the peak, the maximum deformation, and bending stress. So maximum deformation can be calculated from the response spectrum. You watch the first and second video clips uploaded on the Blackboard. So the first video clip I explained about the theoretical background, how we can develop the response spectrum and what those numbers and the values on the response spectrum mean. In the second video clip, I showed you how to use the Prism software so we can easily develop the response spectrum for all three quantities: deformation, velocity, and the acceleration. So here we'd like to know the peak deformation, which is the maximum displacement due to a certain ground motion. And the ground motion given here is the L central ground motion. And we're going to use the response spectrum, especially the combined response spectrum that I introduced earlier. And the corresponding damping ratio to develop that response spectrum was 2%. Okay, so those informations are given in the problem descriptions, but we are not really using those numbers. So that's the problem. Okay, so we'd like to know the peak deformation, and we're going to get it from the response spectrum. Remember, the response spectrum in a basic concept, let's say the acceleration or velocity or this displacement. So this y-axis is going to be the spectral value, spectral acceleration or spectral velocity or spectral displacement, depending on the quantity that you're looking for. And the x-axis is usually the natural period of the structural system in second. Okay, so let's say in this case, we are looking for the peak deformation. So we have to have the response spectrum in terms of spectral deformation. And when we have a certain graph or chart like this, we first have to know what is the period of this structural system. Okay, and the period is equal to 2 pi over omega n, and omega n can be calculated as k over m. And the weight is given, by the way, this 5,200 pounds, this is the weight of this top portion, right? And this mass can be calculated as weight divided by gravity constant g. Okay, so those are the information that we need. So anyway, when you have a period of the structural system, go to the response spectrum for the deformation version. We're going to find out the corresponding deformation, which is the maximum, which is a peak deformation with given period. So that's how we're going to solve this problem. Okay, so before we jump into the response spectrum, I said we're going to use the combined response spectrum given in the textbook. We're going to use those, but we have to first find out the mass and then stiffness to get this natural frequency. And if you have a natural frequency, then you can calculate natural period of the structural system. So let's go over that. Okay, so let's start with the stiffness. So stiffness for the cantilever system, as you can see, this is kind of a cantilever, right? So we have a fixed boundary condition here. The structural member is here, and we're gonna kind of apply the majority of the mass, which is in terms of the weight in this case, is kind of a load at the tip of the structural member. So we can develop the stiffness of the steel pipe as a cantilever. And the corresponding equation for cantilever structural system to determine the stiffness K is 3EI over L cubic. So L is going to be the length of your structural member, 3 is a constant, E is a Young's modulus, and I is a moment of inertia. So all the informations are given in this case. So 3 times 29,000, that is in KSI. So I'm going to using everything in kips for the load and the inches for the length. And then the moment of inertia. So the moment of inertia was given as 7.23 inch to the fourth. So that's good. So we just multiply by 7.23 here. And this is inch to the fourth. Divided by L cubic. L, the length of the structural element, which is this steel pipe. The entire length of this steel pipe is given as 12 feet from this support to the center of this mass. So we're going to use 12, but be careful because that 12 is in feet, and we're going to converting everything into kips and inches. So 12 times 12, that is the conversion factor from feet to inches, and cubic. So that we will have inch cubic here. Okay. Then KSI is a kips per inch square. Inch square is canceled with this inch fourth. So we have inch square here. So we'll have the kip per inch unit for our stiffness, which makes sense, right? And when you calculate this number, I got 0.211 in kips per inch. So this is going to be our stiffness for the structural system. And let's talk about the mass. So mass is, here we go. So let's look at the mass. Mass, we have actually two different masses. One is coming from the top portion, which is 5,200 pounds divided by G. And the other portion is going to be the mass of the steel pipe itself. And the given information said the total weight of the pipe is 10.79 pound per feet. So this is the unit weight of the steel pipe. To get the entire weight, it should be 10.79 times 12, which is 129.5 in pounds. So again, this is the weight, and then we have to divide it by g to get the mass, right? So 129.5 pounds divided by g. So here is one mass for the steel pipe portion. This is the mass of the top portion. As you can see, 5,200 pounds. So just let's forget about this g thing. So let's compare the weight to weight. Then 5,200 pounds versus 129.5, which is kind of small enough to neglect in our calculation. It doesn't really affect to the period of the structural system. So let's just go on and focus on this weight only. Then how can you figure out mass is equal to 5,200 pounds, and the G constant for the pounds is going to be 386. So this is the weight, and this is G. Then I have 0.01347. The unit is kip second square per inch. So we have K, we have M, so that we can calculate this natural frequency, square root of K over M. So when you calculate it, square root of 0.211 divided by 0.01347, and I got 3.958 radian per second. That's the unit for the natural frequency. From there, we can easily find out Tn, the period of the structural system. I got 1.59 second. Okay, so that's how we can come up with the period of this structural system. Based on the given information, we have the moment of inertia, Young's modulus, the weight. I initially compared the weight of the top portion and the weight of the steel pipe as well. And based on the comparison, I ignored the weight of the steel pipe. So we used these equations to find out the natural frequency first, and then come up with the natural period. So natural period of the structural system is 1.59 seconds. Okay, now we can go on to the response spectrum. So let me go over. Let's see. Okay, so I'm gonna just download the file. So under the Week 12 folder, you have this the images from your textbook. You just download it, download this PowerPoint slide, and there is a combined version of response spectrum based on the El Centro earthquake. In the meantime, I'm going to set up this. Okay, here it is. So, okay. So I explained about this theoretical background of the response spectrum before, and this was the combined version of the response spectrum, right? Okay, so oops, let's see. Okay, so as you can see, this is response spectrum. I said the combined version. So the x-axis is here the natural frequency and natural period Tn, right? And the vertical axis is v, which is the spectral velocity. And there are two other x's here in the diagonal side. This is spectral acceleration, spectral deformation. So how can we read this one? So first of all, we have to go on to the corresponding value of our period, which is 1.59. So, and by the way, these are in a log scale. So you have to make sure that you're going to pick the right number. It is not exactly in the middle. 1.59 is going to be somewhere, probably somewhere here. So let's say this is 1.59. And then from there, we're going to draw a straight line vertically. until you meet this graph. So this is going to be the point, intersection point. From there, when you go this way, it's going to be the value in terms of the deformation. When you read the value in this way, it's going to be the spectral acceleration. And then when you go this way, exactly perpendicular to the x-axis, it is going to be, the perpendicular to the y-axis, it is going to be the corresponding spectral velocity value. In our case, we're looking for the peak deformation. So here we're going to go on this way, which is 5.0. So let's see, 1, 2, 3, 1, 2, 3, 4, 5. It should be going here. Anyway, that's how we can read it. So according to 1, 2, 3, 4, 5. According to the textbook, based on the exact number, location 1.59, the corresponding spectral deformation is going to be 5.0 inches. So this is going to be the maximum deformation due to the L central earthquake for the structural system. So that's how we can read. So this is one of the way we can use this combined version of response spectrum. And in order to get the more accurate number for our result, you can always run the prism analysis to develop the response spectrum and make sure that you are reading as V value to get the peak deformation. Okay. All right. So that's the first part of the question. What was the peak deformation? So the answer is going to be 5.0 inches. Now the second part of the question was, how can we figure out the maximum bending stress? So let me go over to the document camera again. Okay, oops. Clear, and then set. Okay, so let me go back to the document camera. Come on. I have a little bit of problem to get a better resolution. Oh, here we go. Okay, so go back to the problem. So the first question was determine the peak deformation. We just got it as 5.0 inches, and that I just explained how to read the combined response spectrum. Now the second part of the question is, what is going to be the bending stress? Remember the bending stress we learned in the strength of material. So when we have the moment given, then we should be able to find out the corresponding stress, bending stress, as sigma. The typical bending stress is negative my over I at the maximum value. When you maximize this y value, it is going to be mc over I. Okay, and this maximum y, which is c, is coming from the cross section. So let's say this is the cross section of our steel pipe, centroidal axis, and y is the variable which is measured from that centroidal axis in a vertical direction. So the maximum value, of course, is going to be the entire radius up to the surface, outer surface. So I can say the small c value is going to be 4.5 divided by 2, because 4.5 was the outer radius, right? I mean, the outer diameter. Did I mention the radius or diameter? I don't remember, but these are the diameters. That's why I use DO. Okay, so this is outer diameter and the inner diameter. Sorry about that. So DO is going to be 4.5 inches. That is the outer diameter. And DI, the 4.026 inches, which is the inner diameter. So the outer radius, which is going to be the maximum value of y, the c, is going to be 4.5 divided by 2. Now, how can we calculate this m value? So here we have equation to find out the force coming from the acceleration, because we all know that F is equal to ma, right? So what if we'd like to find out the corresponding force to the maximum acceleration? Okay, to get that, this A should be spectral acceleration coming from the response spectrum. So let me go back to the response spectrum again. So here we had, let me go back. So here was a 1.58, I'm at 1.59 second, and this is the corresponding value intersecting with this t. Now, when you read this way, then you can have the corresponding value of the spectral acceleration, which is around 0.2. Let's see. Yeah, maximum acceleration is exactly 0.2 in g. So the unit is in g. Okay, so that's how we read the spectral acceleration. So go back to the screenshot. So this SA is going to be equal to 0.2 in g, right? So what is mass? Actually, we already calculated it, the mass, but we don't need to use that number again because mass. How can we have mass? Mass is equal to weight W divided by G. Now we have G here in our spectral acceleration. So F now can be calculated as weight over G times spectral acceleration, which is 0.2 in G, so that G is going to be canceled out. So the corresponding maximum force due to the spectral acceleration is equal to 5,200 in pounds, which is the weight, times 0.2 that is coming from the spectral acceleration. In terms of kips, then now it is going to be 5.2 in kips times 0.2. Then I have 1.04 in kips. So this is the corresponding force. So let's say here we have a structural system again. We have an El Centro earthquake. The maximum spectral acceleration at this mass level was 0.2 in G. So the corresponding force based on that actual force, so this force is going to be inertia force, right? That F is now calculated as 1.04 in kips. Now, what is going to be the corresponding moment? Moment is a force times distance, right? And this distance was given as 12 feet. So from there, we should be able to find out the moment as 1.04 kips times 12 in feet, right? So it's going to be 12.48 kip feet. That is going to be the moment created by this inertia force 12 feet above the ground due to the ground motion excitation. So that moment it is going to be used in this calculation. So finally, we can find out sigma max as moment times c, the maximum value of y, divided by the moment of inertia. So 12.48. So now I'm going to use, I'm going to convert everything into kip and inches. So 12.48 is kip in feet. So I'm going to multiply by 12 to change it into kip inches, which makes sense, right? And is it better? A little bit better? Okay. So this is m times c, again, 4.5 inches divided by 2. So 2.25 divided by moment of inertia. Moment of inertia was 7.23. Then I have 46.5. The unit is, everything is converted into kip and inches, so it's going to be KSI, kips per inch square. So due to the epicenter earthquake, with the 5,200 pounds of the mass on the top, that's the weight on the top of the steel pipe, we expect to have this amount of the maximum stress applied to the outer surface of our steel pipe. So that's going to be the answer for the second part of the question. All right, so this is the end of this video clip, and I'm going to go over to continue to go over the example 6.3, which is the same problem, but now we're going to use a little bit different section to kind of try to strengthen the steel pipe. So replace the steel pipe with a different size and how that affects to the earthquake demand. So I'm gonna upload the next video clip in a minute. Thank you. Bye.